Okay, hello everyone, this is Puya. So let's see how we can implement Deques using the concept of circular array. So as mentioned earlier, Deques are containers that have two ends, two open-ended ends, and then you can insert or remove data from both ends. So this is like something similar to what I have drawn here. The main four operations that we want to implement are insert at front, insert at rear, remove from front, and remove from rear. So these are the main four operations that we want to implement. The rest of the operations are going to be easy once we implement these ones. Everything hopefully makes sense. If you remember, like when we talked about queues, we already implemented insert rear and we implemented remove front. Okay, so you remember that here what we did when we wanted to insert at rear, what we did, we just like incremented rear all the time, and here when we wanted to remove from the front, we incremented front. But because we have a circular concept, once you reach the end of the array, right, what we did, instead of just incrementing because we're going to get out of bound, once we get to the end of the array, we reset the index to 0, both for the front and the rear. So I'll implement them anyways, though you have seen them before, but it's going to be a good review. But once, like now that like I wrote these main four operations here, just wanted to show you that when you want to insert from the front, what's gonna happen is your front, it's gonna be moving towards the left, and once you're gonna be removing from rear, your rear would be moving towards the left. When you insert from the rear, your rear moves to the right. When you remove from the front, your front moves to the right. When you insert from the front, let's say like if this is our front, if we want to insert, then this becomes the front. So your front is moving towards the left. And the same here, if this is your rear and if you want to remove from rear, your rear is going to move to this index. So your rear is going to move to the left side. So keep this in mind, and we're going to implement first what you guys are familiar with. So let's just do insert rear. I hope I don't make any mistakes. I'm just gonna write a pseudocode here. Okay, so first thing that we want to check if because we want to insert, right? So we want to make sure that our deck is not full, right? So how can the deck be full? The deck can be full if this is the case. For example, if this is our rear and this is our front. This is one case that the whole array is full. But there is another case that the deck can be full. How about this case? If front is here and rear is here. Okay, so in this case also it means that we have started from here, we filled everything, we circulated around the array, and we inserted at these points, and now the rear is here. So in this case also the deck is full. So writing the condition, as you guys remember that, I can do it two ways. I can say if front is equal 0 and rear is equal n minus 1, or front is equal rear plus 1. I can write the condition this way. But you saw that we can write it another way, right? We can write it in the case that if front is equal to rear plus 1 mod n, or mod size, right? If that's the case, this is going to cover both cases, this case and this case, right? In this case, rear plus 1 mod n, it's going to be rear plus 1, and it's equal to front, so it's going to know that the deck is full. In this case, rear plus 1, it's going to become 5. 5 mod 5 is equal to 0, so these two are going to become equal. We know that this is going to be full deck. So if that's the case, this is a pseudocode. This is not a C++ program, so I'm just going to write it this way so that you don't get confused. You can print a message, and you can just like return or throw an exception or whatever. So we check that our excuse me, our deck is not full. The other thing that we want to check here, because I'm returning here, I can start with an F. Otherwise I should write else if, but it doesn't, like if I get to this point, it means that this condition was not true. So what I should do, because you remember that when we want to insert from the rear, we only have to increment rear. But there is one case that we also have to change the front. If both front and rear are equal to -1, right? You remember that we initialized both front and rear to -1. This represents an empty deck. So if front is equal -1, right? I'm just gonna write this one, but this is optional. It's not actually needed, but just to give you perspective, I write this. If both of them are equal to number -1, that means that the deck was empty and we are inserting the first number. So in this case, what do we have to do? What do we have to do? Both front and rear are gonna be 0. Yeah? So it means that we have inserted inserted the number here, and both front and rear are pointing to the same, or like are equal to the index 0. Okay. Do we have to check another condition? No. Else, we said that we wanted increment R, or the rear, but there was one problem with that. What happens when R have reached to the end and the array is not full? Let's say the front is here, right? So if you want to increment R, it's gonna get out of the bond. What we don't want to get out of the bond, we want to circulate back and come to the beginning of the array, to the start of the array. So this is not gonna work. How do we do that? We said R is equal to R plus 1 mod n, right? This is gonna be similar to R equal to R plus 1 if R is any of these indexes except the last one. If it is equal to the last one, then R becomes 0. Okay, so that's how we fix the problem. So we found the correct indices for front and rear, the correct values for front and rear. So what we just need to do, basically say A rear. Why did I do everything capitalized? I should just, like, I'm just gonna do everything lowercase so that we are consistent. AR is equal to X, the number that we wanted to insert. So this is how we insert from the rear. I hope this makes sense. We did this before. I hope I haven't made any mistakes. Oh, sorry, I'm missing an equal sign here. So we checked if the deck is full. If it is full, we can't insert any other number. If it is empty, it means that we have to change both front and rear. Otherwise, we only need to change the rear. Okay. So that was how we can insert from the back of the deck. Okay, so let's just like see the other one, the other option that we have for inserting. Insert from the front. Okay, so basically what we want to do, we want to say that AF is equal to X at the end, or whatever the name of the array is. Okay. So again, what are the cases that we have to check if the array if the array is full or if the deck is full, right? So we can write the same condition that we had before, right? If basically rear plus 1 mod n is equal front, means that the deck is full, right? The array is full, so we can't insert any number. You do the proper action, you take the proper action that you want to take here. You can also write this condition different way. You can say that if front is 0 and rear is equal n minus 1, or front is equal to r plus 1, then we know that the array is full. But it would just, both those two conditions can be summarized into this format. Okay, so once we pass this if, it means that the deck was not full, the array was not full. So again, we want to make sure if this is the excuse me, if this is the first insertion that we want to do in the deck. If that's the case, if front is equal -1 and rear is equal -1, this is optional, then we just want to say front and rear are both equal to 0. Okay. Then let's just like write something like this. Let's say like we have this array 3, 4, 5, and we want to insert from the front. So otherwise, what we want to do, we just basically want to say f is equal to f minus minus. We want to move f and insert another number here. Okay, so that's what we want to do, right? So this is like how we can insert. You remember I said that when you want to insert from the rear, you increment rear, you move rear towards the right. When you want to insert front, you move the front to the left. Okay, but can this cause any problem for us? What if we have a case like this? 3, 4, 5. This is the front, this is the rear. And I want to insert from the front. Is that possible? Yes, it is possible because this is empty, right? But the index for it is 4. It's not -1, right? So we can't write it like this. Okay, so you can write two conditions, else if front is equal to 0, make front equal to n minus 1, else f minus, let me write it like this, else if front is equal 0, make front equal to n minus 1. We know that the array was not full, so we know that there is a space here, else f minus minus. So this is one way of writing it. I can also reduce this to something like this. You remember that if it is 0, we want it to become 4. If it is 1, we want it to become 0. So for any other number other than 0, we just like gonna be decrementing. If it is 0, we wanna make it n minus 1, right? So you can write this in this way, f is equal to f minus 1 mod n, right? The same way that we did it for the insert from the rear, but the problem is that like this is going to be a negative number, right? So some people are not very comfortable doing mod operation for negative numbers if the f is 0. So I'm just going to add an n here, right? You know that if I divide 2 by 5, the remainder is going to be the same as the remainder of 7 divided by 5. It's going to be the same as the remainder of 12 divided by 5. The same remainder as 17 divided by 5. If I add 5 or multiples of 5 to any number, the remainder doesn't change. Okay? So you can replace these lines with this one. F is equal to n plus f minus 1 mod n. Okay? For any number other than the 0, this is going to be the same as f minus 1, minus minus. It's going to be equal to f minus 1. If it is 0, then this becomes n minus 1. Okay, so that's how we can insert from the front in a circular array. So this is the implementation of insertion. We did both of them. We did insertion from the rear, and we did insertion from the front. I hope this makes sense. It's okay if you want to write it this way with 2 conditions, or if you want to merge them into just like one statement. Okay, both of them are okay. And at the end, we want to insert from the front. We change the value of the front. You see that like most of the time we only need to change the front, except the case that this is the first number that you want to enter. In that case, we want to make sure that we make both front and rear equal to 0. Now, the next operation that I want to show is how to remove from the front. Again, I choose this one because you already have seen this. Where did you see this? When we implemented Q using circular array. We already did that. Okay? Excuse me. So, when you want to DQ, when you want to remove, what is the precondition? What should we check? We should check if the array or the deck is empty. If it is empty, we can't DQ anything. We can't remove anything, right? How do we know? If f is equal -1 and rear is equal -1. Again, I'm gonna emphasize on this that this is optional. If you implement your methods properly, this one is gonna be sufficient. If that's the case, see out something and you can just return or throw an exception. Right? So we checked if the array is not empty, right? So we get to this point. Now, here when you're removing from the front, if this is the front, it means that you're moving the front towards the right side. So we want to increment front. Most of the time we don't need to change rear, right? Unless if front is equal rear. If that's the case, what does that mean? If front and rear are the same. If front and rear are the same, it means that we only have one element left in the deck, right? And this is gonna be the last number that we want to DQ, we want to remove. So then after this removal, the deck becomes empty. So we want to make sure that we change the value of both front and rear to -1. Okay? Make sense? Excuse me. Okay, so we did the check for if this is the last number. Otherwise, if this is not the last number, what do we want to do? We want to increment the front. We want to increment the front. But again, this might cause a problem when you have a case like this. Let's say that you are like this. This is our 2, 3, 4. And this is, how is this gonna cause a problem here? Here, yes. Let's say that this is our front and this is our rear. It's possible, right? We have a circular array, so it is possible for the front to be here, right? And then we have 2, 3, 4, and 6, right? Then in this case, we want to move front to the right, right? We want to remove this one and make this one front. But I can't do front plus plus. What should I do? How can I fix this? I can write this as front is equal to front plus 1 mod what? Mod n. Right? So this is most of the time in this case, in this case, in this case, in this case, this statement is similar to f++. Only in the case that front is here, because we are in a circular array, we want to move the front to number 0. Again, you can write 2 else if front is equal n minus 1, then make front equal to 0, else f++. But this statement does the job for both of those conditions. Okay, so this is like how we remove from the front of a circular array in a deck for implementing a deck. Right? Again, like we checked if the array is empty or not. We checked if this is the last number we want to remove. If it's not, we only have to change front. Right? And we move front towards the right side. The only time that we have to change the rear is when you are removing the last number in the deck. So I hope this makes sense. Now let's implement the last function or the operation. Remove from the rear. Okay, so if I want to remove from the rear, if I remove this one, it means that this becomes rear. So we want to move rear towards the left side. We want to decrement rear, right? But again, we have to check first if front is equal -1. It means that the array is empty. We can't DQ. So you either have to return or throw an exception, print a message, right? You can't remove. There's nothing to remove. If front is equal to rear, If front is equal to rear, again, this means that you only have, let's say this is the case, means that you only have one number left in your deck. You're going to remove it and the deck becomes empty. So you have to make both front and rear equal to -1. Because after this removal, both front and rear become -1. Okay. What else? What we want to do, as I said, we want to move rear towards the, excuse me, towards the left side. So we want to do rear minus minus. Okay, so this would work in this case, right? This becomes rear, right? But what if we have a case like this? I'm sorry. This is front. We start from here, 1, 2, 3, and then rear is here. I can't do rear minus minus because 0 becomes -1. We don't have any index -1. So again, I can do it like this. Else if rear is equal 0, right? This is not going to be rear. This is going to be rear. So rear is equal to n-1. Else, now if this is rear and we want to do it one more time, else just like we have to decrement r. But this is similar to what we saw earlier, right? I can just replace this part by saying that r is equal to r minus 1 mod n. This is okay, but just like so that we don't have to deal with negative numbers, I'm gonna add an n to it. So you can replace this part to here, right? If r is equal to 0, this term becomes r equal to -1, n minus 1. Otherwise, it's gonna be the same as r minus 1. It's gonna be just this. Okay, so this is how we can implement these 4 operations: front, rear, and inserting from the front, inserting from the rear, removing from the front, removing from the rear, using a circular array. Now, in the next video, I'm gonna show you how to implement the deck using a linked list. Okay. So you guys are already familiar with the concept of single linked list. When each node has one pointer connecting, one pointer element that connects it to the next node, right? And you remember that in single linked list, we only can traverse from one side to the other end, right? We can't go back, right? So here you would see that we have a head pointer, it will go to the next one, and so on, right? But you saw that when we want to implement a deck, we have to change both. Like if we have 2 pointers pointing to both ends of the linked list, excuse me, we need to be able to traverse through both directions. It's not just like going from left to right. Sometimes we have to go from right to left, right? If we are inserting from the front and removing from the rear, for example, right? So, in order to implement decks using linked list, single linked list would not work for us. We have to use what is called a doubly linked list. So what is a doubly linked list? In the doubly linked list, this is what we had in the single linked list. Integer data and node star next, right? We had one data part, one pointer part. In double linked list, each node has two pointer, one pointing to the next node, one pointing to the previous node. So you see that this one are pointers. This is the data part. This is the pointer, this is the pointer, this is the pointer, this is the pointer, and these are the data types. So what we have is that the next pointer of each node points to the next node, and the previous pointer of each node points to the previous node. This one is done. This one, it's gonna be like this. Okay, how about this one? Right, the previous pointer of the first node, it's gonna be the null pointer. The next pointer of the last node, it's gonna be null pointer, right? So this way you can just traverse in both directions, like a double-sided street, right? So you can just go from both ends towards the other end. Okay, so this is the concept of doubly linked list. First of all, you should be familiar with this one. So this is what we're going to use to implement a deck using linked list, right? We can't do it with a single linked list. We're going to do it with a double linked list. Okay. Also, before I go any further, you might also hear of the concept of circular doubly linked list, as we saw in the concept of single linked list. We saw a circular linked list, right? If it is circular, it means that instead of this being 0, it's just gonna point to the first node, and this one, it's gonna point to the last node. So there are two pointers connecting two nodes, right? That's why it's called double linked list. Okay. So, but this is only when we want to have a circular. Let me write this one. Remove this single. This is if circular. Otherwise, these are gonna be 0. If you want to make it circular, they're not 0. This pointer, it's gonna point to the first node, and the previous pointer of the first node is gonna point to the last node. We make it a circle. We wrap around. Okay. So, excuse me. So again, let's just start. We're gonna have two pointers. Let's call this one front, this one rear. Okay, what do we initialize them with? When the deck is empty, null pointer. Okay. And let's now see what we want to do if we want to insert from the front. Okay, so first of all, you remember that in the linked list, we allocate as we need, right? We never have waste of memory, right? So if you want to insert a node, first you have to allocate it. Okay, so like we don't have to check for the deck to be full or not, because, well, we don't have any limit like arrays. We don't have a size. We allocate as we need. The only problem that we might encounter is running out of memory, not having any heap memory available. But otherwise, we just have to allocate a new node. So let's do that. I'm just gonna do it here. Node star temp, it's equal to new node. So we have a new node here, T, which is like, this is T. This is pointing to the new newly allocated node. It has the previous pointer, next pointer, and a data part. Okay. What do I want to put inside the data part of it? T arrow x is equal to, sorry, T arrow data is equal to, I already gave you the answer, it's equal to x. Whatever you want to insert, that's the data, right? That's where it goes here. Okay, let's just like initialize both the next and previous pointer to 0 for now. Okay, so in this case, let's say that we want to insert 5. So 5 goes here, and these two pointers are 0. They're not connected to our linked list at all. Okay. So if I want to insert this node at the front, you would see that here only front needs to be changed, right? Only front needs to be changed, right? So what I have to do, I'm gonna write the wrong program first, and I'm gonna ask you to complete it with me. So what should I do if I want to move this one here? So first of all, like, it means that this node should become the front of the linked list. Means that this pointer should point to the previous front. So how can I write that? I'm gonna write it here. T arrow front. Oh, sorry, T arrow next is equal to front. Okay. What else? What else should I do? Right, we made one link between these two nodes. Right, what is the other link? The previous pointer of the front should also point to this newly allocated node. So F arrow previous is equal to what? I want this pointer to be pointing to where this pointer is pointing to T. Okay, so now I move this one before here. Now this is our front of the linked list, right? So I have to say front is equal to T. This is not front anymore. This is front. Done. Does that work for all the cases? Do I only need to change the front for all cases? What if this is the first number I want to enter? I want to insert. My rear is null pointer, right? And I'm not changing it here. But when I insert this, both front and rear are going to be pointing to that node. Okay? So I have to check that case. If front is equal null pointer and rear is equal null pointer, if that's the case, what should we do? We just like have to say that we already put the data there. So like we don't have any linked list. We allocated this node. We put 5 here, we put 0 here, we put 0 here. So we only need to do just making sure that both front and rear are pointing to this node. So front is equal to rear is equal to T. Okay, so that's the only thing we need to do when we want to insert from the front. So just remember that the difference between single linked list and double linked list is that between each nodes we have 2 pointers, right? Not only you have to make sure that the next pointer of the previous node points to the next node, you also have to make sure that the previous pointer of the next node points to the previous node. Okay, it's a little bit confusing at the beginning, but like you get used to it. Is everybody okay with this? Hopefully that's the case for you guys. I hope everybody was okay with that. What if we want to make this a circular array? Think about that. If we want to make this a circular array, anytime we change F and R, we have to make sure that R arrow next, instead of being 0, would be pointing to front node, and F arrow previous is pointing to the rear node. If we want to make it circular, so you just have to enter this one here and here, both cases. Okay, so this would go both here and here if you want to make it circular. A circular linked list. Otherwise, this is like if you just want to have a linear double linked list, this would just implement the insertion from the front. Now let's do insertion from the rear. Okay, I'm actually not gonna change this part. I'm not gonna change this part. I'm not gonna change this part. I'm not gonna change this part. Not this, not this. Only this part I have to change. Because now this is my front, this is my rear, and I want to insert from the rear, right? So I only have to change the rear. The only time that I need to change the front is if this is the first number I want to insert. Okay, if that's the case, what do I need to do? I have already allocated, right? I have put the data in this new node. I have initialized both of the pointers of this new node. Now what I have to do, first make sure that R arrow next is gonna point to R arrow next, which is this one. I wanna make it point to this new node because now this is gonna be the rear of the list. So R arrow next is equal to T, right? So we made one link between these two nodes. Okay, what is the other link that we have to make? We have to make sure that the T arrow previous is pointing to rear, the previous rear. Okay, and now like our linked list has a continuation. It comes all the way here. This is not 0 anymore. This is not 0 anymore. Or sorry, is this 0? This is 0. This is not 0. This is the previous. This is not 0. This is still 0. So now this is the tail of the linked list. We just have to make sure that we say that R is equal to temp. Right? So now this is not going to be the rear of the linked list. Rear is going to be pointing here. Okay. Again, if you want to make sure that this is a circular linked list, right? Instead of these two pointers being 0, you have to change them. You have to make F arrow previous point to the rear and rear arrow next point to the front, as shown here. Good? I hope that makes sense. Let's just continue. Okay, I'm just gonna write this one again here, front and rear. This is 0, this is 0. If you want to make it circular, this is pointing here. This is going to be pointing here. Okay, so now let's write remove from front. if that's the case, you remember that we already implemented this one, remove from front, when we implemented queues using arrays, or using linked list or circular linked list, right? You remember that we need to have a temporary pointer. Why do we need to have a temporary pointer? Because we need to deallocate. When we're removing a node, we need to deallocate, right? Because these are like in the dynamic heap memory, right? So we like the deallocation is on us. We have to deallocate. So if we lose this pointer that points to this node, then there is no way to deallocate it anymore. So what we do, we usually have a temporary pointer. We initialize it as f, because now we want to remove the front. So we want to make sure that this pointer points to the same head node, right, as the front, right? So that when we make front point to the next one, we don't lose this node. We still have track of it using this pointer. So now, okay, so when you want to remove, now you have a precondition, right? Because you can't remove from an empty deck the same way that you can't remove from an empty queue or empty stack. So first we have to make sure if front is equal null pointer and rear is equal to null pointer, then like do the proper action here, take the proper action here. Okay. What's gonna happen if, so you see that here, like we want to remove from the front. So we just like need to make this front point to here. That's the only thing we need to do, right? But what if this node is the last node? What if we have something like this? Both front and rear are pointing to the same thing. In that case, we also have to change the rear, right? Most of the time, we only need to change the front, but if we remove the last node, we also have to change the rear. So we have to check whether this is the last node or not. So I'm just gonna write if front is equal rear. That basically shows us that we are removing the last element out of our deck. So we have, then after this, our deck is gonna be empty. So we're gonna say f is equal to r is equal to what? Null pointer. Okay. Else, this is not complete, right? We are like changing f and r, but we also have to deallocate. We're gonna deallocate here. I'm just gonna write it so that we don't forget. Delete t. Once you change everything, once you change front, we're gonna delete t, right? Delete the front. Else, what do we need to do here? We're just gonna say that f is equal to f arrow next. So f, which is this one, this pointer is equal to this pointer. It means that this pointer is going to point to the same place that this pointer is pointing to. So it's not going to point here. It's going to point here. Okay. Are we done? We are not done. We still have to do one more thing. Because now this is our front, right? This is not part of our linked list anymore. We are going to delete it later, right? We can remove it later. But one thing is left. This pointer is still pointing to the previous front. So we have to change it. Now, do we have access to it? Yes, because now this is going to be f arrow previous. What do I want to make it? I want to make it 0. I want to make it null pointer, right? Yeah. So we make this one 0. and then we delete T. So whatever T is pointing to, we're going to delete this. Okay, so now this is our linked list. This is our new front. This is our rear, and we delete T, right? Some of you ask me, like, what's going to happen to these pointers? These pointers are static memory, right? They're going to be deallocated by the end of the function call, right? We only have to take care of the dynamic memory. Okay, I hope everybody was okay with this part. Like, we checked if the deck is empty or not. We checked if we have to change the rear as well as the front, if this is the last element we want to remove. Otherwise, we just have to move front one to the right. Okay, so F is equal to F arrow next, and make sure that the previous pointer of the new front, it's going to be a null pointer, so that we know this is the front of the list. Again, if you want to make this a circular linked list, you have to do these two operations, right? Both here, like just here. So like instead of F arrow previous to become rear, it becomes a null pointer, it has to become rear, and rear arrow next has to become front. So you have to do these two operations here, like in this case over here, to make it a circular linked list. If you want to make it the linear linked list, this is not needed. You just have to make sure that this is null, and this is already null. Now, finally, remove rear. Okay, so for the remove rear, I'm not gonna change anything here. I'm only gonna change this part. It's that easy, right? So here, this is gonna be no the start. Now we want to remove the rear, so we make this temporary pointer pointing to the rear. Okay, if we check if the deck is empty or not, we check if this is the last number we want to remove. If that's the case, we need to change the front as well as the rear. Otherwise, what do we need to do? We want to move rear one to the left, right? We want to remove this one, so this should become our rear, right? So what should I do? What I should write is rear, which is this pointer. It's going to be equal to this pointer. What is this pointer? Rear arrow previous. It means I want this pointer to point to the same place that this pointer is pointing to. Okay, so then R is not pointing to here, it's going to point to here, right? And that's why we need this temporary pointer, because as soon as this statement is executed, R is not pointing here. We need to have a pointer pointing to this node so that we can deallocate it later. Okay. So this part is done, right? And eventually we're going to delete T. So this is going to be also gone. But this pointer is still pointing to the previous rear of the linked list. So what I should write now, this pointer is now called rear arrow next is equal to null pointer, to make this one a null pointer. Okay, so this is how you can remove from the rear. Again, if you want to make this a circular linked list, instead of this, you would just do this part, and you would have R arrow next, which is this one. Now, this case, this is interesting. R arrow next, which is this pointer, it's going to point to this node. This is going to also point to this node. If you make this one a circular linked list, one node, two pointers pointing to the same node. If you want to do that, you have to add these two statements to whenever you change front and rear. Okay, so that's all about implementations of Deques using circular linked list or linear linked list, and we also covered circular array implementation. I hope that makes sense. If you have any questions, please leave comments or email me. Thank you so much. Bye-bye.